Next, we are going to look at another way to drive high power out of the chip. Using power mixer. So far, we have seen that to generate high frequency signals, we need a mixer, and the mixer is going to be effectively a transconductor driving generating the baseband current, which will be going to a switching circuit. And we can see a double balanced circuit. So in the double balanced case, we have a switching quad. The input is the baseband input. Here we have, let's say, LOP. This is LOM. Again, the load is going to be a tuned load because we are generating an RF signal. This is our double balanced active mixer for a frequency up conversion. Now here, one point to note is that these blocks are this transconductor, very similar to the amplifying element in the case of a driver amplifier. Okay, so take a voltage and then they're converting into current. So the idea is, if already we have this transconductor as a part of the power mixer, why can't we size these transconductors such that they can drive high amount of current? And keep in mind that this current is going to be baseband, a low frequency current, but with the help of this switching quad, we can take this high power baseband current and move it to RF frequency so as to directly drive a load with high power. So the motivation is that now we don't have to design one more circuit cascading a mixer, and at the same time we can see that since these transconductors are now operating at baseband, so the design of these transconductors can be simpler. Their layout is going to be easier as compared to the case when these transconductors are operating at the RF. So starting from a simple double balanced mixer, so this is a double balanced mixer. Can make few modification and adapt it to directly generate high power RF output. So one important modification we can do here is we can add a cascade element so as to shield the input transconductor and these switching elements from the high output swing. Okay, so instead of directly connecting the output of this switching quad to the load, we can add a cascade element. This is the cascade, and here is the switching quad. And although it is not shown here, but we know that if we are designing a quadrature mixer, then we need to have a replica of this mixer, which is driven by a quadrature LO, and the outputs of this in-phase mixer and the quadrature mixer can be directly connected in the current domain, so as to have the combining of the in-phase and quadrature phase signal and directly drive this load. And one point to note here is when we are talking about this power mixer, the motivation is to simplify the design of these transconductors, in the sense that not only the layout we have to be concerned about when we are trying to drive a high power signal, even the non-linearity of these transconductors are going to directly affect the output performance. You have seen that when the signals are having amplitude modulation, then it can result in a spectral regrowth if the transconductors are not linear. So good thing is when we are operating in this manner, these transconductors are actually handling baseband signal, so low frequency signal. So we can apply this low frequency techniques using op amps and feedback to improve the linearity of these transconductors while also operating them with an efficient biasing. This is power mixer. Idea is conductor layout and linearity engineering is simplified as it is handling baseband signal. Using this kind of approaches, it is possible to generate 10 to 15 dBm kind of output power. Instead of using a mixer and a driver amplifier separately, we can just use a power mixer where there is an opportunity to improve the design of the transconductor.